So embedded electronics, this is an interesting one. So the basis of our original concept when we set the company up 5 years ago, and the PhD that predated that, was using this process called print pause print, which is fairly common knowledge, and only certain printers allow you to do this. You can put it back in, print the lid directly onto it, and that's how you get your fully sealed microfluidics. And the knowledge of how to use that material, that's our specialty. That's what we can do really, really well. We know what material it is, we know how to apply it, we know how to remove it. We don't always use it though. As printers have got better, it's less applicable. It certainly doesn't work with circular cross sections and complex geometry. But that pausing process allows us to do other things. So as I say, we can put glass components in there, we can put flexible membranes in, we can put electronics in. Knowing that electronics are really useful especially for electrobiosensing, electrochemical biosensing, we thought, well, let's try and put a PCB in that. And because we've got some larger format printers, we thought, let's put it into a well plate. So if this video played, and I think it's on our website, it demonstrates a very customized well plate. So the left hand side there is wells of a 96 well size. We've got 16 and 32 well sizes in there as well. We've got micro channels between the wells. The PCB is wired up to a control system that detects fluid. It's got fluid detection, it's got heaters, it's got thermistors as well to monitor the temperature. You've got light sources, and you've got an open well in there as well. So we're trying to promote, you don't have to be restricted to the layout of a well plate, but you can still use a well plate reader to run your particular experiments. Obviously, as we are embedding the electronics in that, we can have the fluid directly in contact with the electronics, or we can insulate it and embed it slightly within the resin itself. So let's say you've got electrical insulation now as well. And then we get onto my favorite stuff, the anatomical models. These things are amazing. This came, actually, if those of you who follow me on LinkedIn, you'll see I posted about this recently, because quite a lot recently. It came originally from creating a leaf model that came from the idea of, can we avoid using straight lines? Can we take a sketch, turn it into a 3D STL, and 3D print that? And we started off with taking an X-ray of a leaf to generate the microfluidic channels of a leaf venation. That got the attention of people involved in vascular systems, and that opened up further opportunities. So the model at the top there is actually a prostate. It's taken directly from an X-ray. We've converted the X-ray to monochrome image, black and white image, and then converted that into a three-dimensional circular sectioned STL file that we've 3D printed. The one at the bottom, it's called, if I can get the Latin right, Meta mirabilis. It's a vasculature network, I think, in the brain, which is for research, R&D purposes, of research chemicals going in through the vasculature. And at the moment, it's you can only use it on a live brain, which means using lab animals. So in the move to reduce lab animal testing by 3D printing these shapes, which come directly from a CT scan, we can create the vasculature networks for research. The channels that go across the middle, if you imagine that sort of H-shaped, the channels that go across the central bar, they're 250 microns in diameter, fully circular and all over the place. These things are brilliant. Absolutely love them. We've done kidneys, we've done livers, we're working on the heart model at the moment, and it really shows what you can do with 3D printing that you simply cannot make any other way.